Hello, world. Good morning, good afternoon, good evening, depending on where you're viewing us from. This is the Fiber Channel Industry Association webinar for Inside a Modern Fiber Channel Architecture Part 2. This is our second in the series. And with us today, we have our illustrious cast, Patty Driever, David Peterson, and Craig Carlson, all members of the Fiber Channel Industry Association in T11, and here to talk to us today about all of our second part of our information about the modern fiber channel architecture. We have a little housekeeping we have to do here, which is let you guys know, if you're not already aware, the Fiber Channel Industry Association, we're a nonprofit, mutually beneficial, international organization of the manufacturers and integrators and users of the technology. And our job is to help promote and educate the industry about fiber channel. We've been around for a little bit more than 25 years. We're comprised of industry-leading companies, which many of you would recognize. And since 2001, we have updated this graphic. We have over 142 million FC ports shipped into the market space. We have a lot to cover today, and we're going to let Dave Peterson pick it up from here. I think that's right, Dave. You're going to take it up from here. You want to talk about the agenda?
Yeah, that's fine.
All right. And with that, ladies and gentlemen, Dave Peterson from Broadcom.
Hello, everyone. Yeah, we have quite a few slides, so I'm going to be going pretty quick through my stuff. So I'll be starting out with building blocks and go through frame sequence exchanges protocols. Then Patty is going to dive into information units, segmentation, reassembly, and cover error detection recovery. Then Craig's going to follow up with current enhancements. So let's get started on part 2. Fiber channel building blocks are frames, sequences, exchanges, and protocols. This diagram here illustrates the relationships at a high level. Frames, sequences, exchanges, protocols. The frame contains the information, i.e. the payload that is to be transferred. Sequence is made up of one or more data frames, and if applicable, corresponding responses. Exchange is made up of one or more sequences flowing in a single direction from the originator of the exchange to the responder, or in both directions between the originator and the responder. And prior to use by a ULP for data transfer, the fiber channel has to be set up for the operating environment. And to do that, fiber channel operating environment is set up by performing fabric login and import login. And both of these logins, once both of these logins are performed, then an FC4 protocol may start using the fiber channel until one or both of those logins are invalidated. And each login using an exchange has a mechanism to accomplish the login function. And again, data transfer is performed using an exchange as the mechanism with the related FC4 translating the ULP protocol to the FC2 level protocol. And, all right, so diving more into frames. Frames are categorized as data frames and link control frames. And for data frames, we got classified as link data frames, device data frames, and video data frames. And for link control frames, they're classified as acknowledge frames. We call them the ACK. And we got link response frames. Those are busy and rejects. And we got link control command frames. Fiber channel frame is based on a common format. And here's a good diagram of that. So we have an SOF, and we got 0 or more extended headers followed by our frame header. There's our data field, the payload. And we got a CRC. The CRC covers any extended headers, if any, the frame header and the data field, and it follows up with an EOF. So a little bit on the EOF. We got the start of frame delimiter precedes the frame content, as we can see here, and there's different SOF based on the class of service, i.e. class 2, class 3. Then we got the EOF, follows the frame content, and then we got different EOFs based on the function i.e. is the frame valid, is the frame content invalid, or is the frame corrupt? Okay, then diving into extended headers. We got 3 flavors here I've listed. We got our virtual fabric tagging header that allows VN ports to share the same physical link while connected to different fabrics. Then we got an inter-fabric routing header, the IFR header, and that's used at every inter-fabric router to route frames towards the destination fabric. Then we also have an encapsulation header, and that's used to transfer frames between inter-fabric routers when they're connected through intermediate fabrics that do not support the IFR header. All right. Then we move into the frame header. See, here's the format here, pretty canned. We got 6 words at 24 bytes. And we'll dive into the fields here. So we got our first one is our routing control, which is actually split into 2 different fields. We call the routing field and the information field. And that further parses out into device data frames. We got extended link services. And I got a reference. You see those in LS5. Then we got FC4 link data frames. And reference to there, you just got to go to your FC4 standard. For example, that'd be FCPE, FCNVMe, and SB6 in this realm. Then we got video data. And for some people don't know that FC is still used for post-production video editing quite heavily, I believe. And you can see that in FCAV and the related AR Inc. 818 protocol that is based on FCAV. Then we got the extended headers we talked about, and basic link services, link control frame, and extended routing. And this one actually struck me by surprise again, because I'm not aware of any standard usage of that, guy. So, but anyways, it's in there. I'm not aware of anybody using it. All right, so then we got our address identifiers, the DID and the SID. The DID contains the address identifier of the destination endport, and likewise, the SID contains the address identifier of the source endport. And each endport has a native endport ID that is unique within the address domain of a fabric. And moves us into the class-specific control / priority field, where the meaning of this field is controlled by a bit. That's in the F control. That's bit 17. We'll hit that in a bit. And if that bit is set to 0, then the bits are CS control information. And there's the table that we have there. So we got preference and we got differentiated services code point information. And if the bit is set to 1, then the bits are interpreted as priority information. So we got a bunch of bits for priority, and we allocated a bit for tagging extension. And let's see, that moves us into the type field. And the type field identifies the protocol of the frame content for the data frames. Again, we got the link service, which are basic link services, extended link services. Again, we got our video data, then we got our FC4s. And there's a list of our common FC4s. And it goes into frame control. That's F control. And that contains control information relating to the frame content. So we got our exchange content, our exchange context, sequence context. And we got our first, last, and end sequence bits. And there's our CS priority bit. And we got a sequence initiative bit. We got act form bits. We got abort sequence condition bits. A relative offset present bit. We got an exchange reassembly bit. I'm not anybody using that one by myself again either. Then we got fill bytes. That moves us into the sequence ID, where the sequence ID field is assigned by the sequence initiator. And this is tied to the sequence ID unique per exchange bit, which is in the PLOGI request. If that's set to 0, then the sequence ID is unique among all currently open sequences between the sequence initiator and the recipient, independent of the exchange ID. And if the bit is set to 1, then the sequence ID is unique among all currently open sequences with the same exchange ID. And both the sequence initiator and the sequence recipient track the status of the frames within the sequence using fields within the sequence qualifier. The sequence qualifier is basically a composite of the SID, the DID, the OXID, the RXID, and the sequence ID. And that brings us into the data field control field, where that specifies the presence of optional headers at the beginning of the data field that we talked about. And again, that's our ESP header. We also have a network header. I'm not aware of anybody using a network header, but they might be out there. And we also have a device header. And one note there is the use of optional headers reduces the size of the user data, i.e. it cuts into the payload. And here I threw in an example of the ESP header. So here's the format of an FC frame with end-to-end ESP header processing. And pink stuff indicates that these fields are set to 0 for ICV computation, if you're interested. But the ESP header adheres to RFC 4303 with the exception of integrity check value coverage. And how to use ESP and FC is specified in FCSP2. And I think Craig might be talking a little bit more on that down the road here in this slide. And I threw in the application header as an example for a device header. This header is constructed as a 16-byte device header. So we got 4 words there, and it's supported as determinate import login. That's our PLOGI. And all we have right now is the destination applicant identifier or source application identifier. And I think Craig is probably going to have an example on that too. All right, we're getting to the end of the frame header fields, and it brings us into the sequence count. The sequence count indicates the sequential order of data frame transmission within a single sequence or multiple sequences within the same exchange. And I think Patty's got some examples on that too coming up. And brings us into the originator exchange ID. That's our OXID. That identifies the exchange ID assigned by the originator of the exchange. And again, the originator exchange block is associated with the OXID, and it's used to track the progress of a series of sequences that comprise the exchange. And we got the responder exchange ID. That's our RXID. And this is assigned by the responder to provide a unique, meaningful identifier at the responder for an exchange that is established by an initiator. And the value of all F's in the RXID field indicates it's unassigned. And again, I got the responder exchange status block associated with the RXID used to track the series of sequences. And this is the last field in our frame header, and that's the parameter field, and it has different meanings based on the frame type. And for link control frames, it's used to carry information specific for the individual link control frame. And for data frames with the relative offset bit present, set to 1, it indicates the relative displacement of the first byte of the payload of the frame from the base address as specified by the UOP. And for data frames with relative offset bit present set to 0, it's interpreted in a protocol-specific manner that depends on the type of IU carried by the frame. And I threw an example in here would be a task retry identification that's specified in FCP5. And we also have the similar thing. It's called Solaire qualifier. That's specified in FCNVMe2. All right, so that gets us through the frame. That brings us into sequences. We already talked about a little bit of that. It's a set of 1 or more data frames. There's just an example of a sequence consisting of frame 1, 2, 3, and N. So it can be N number of frames. And I threw in an example here. This is kind of an example diagram of a read type operation. If you look at it from a high level, where you get like a read command, and here's our data coming back. This is using continually increasing sequence offset. That's the 0, 1, 2, 3. And the next slide is an example diagram of a write type operation where we get a write type command. We got a transfer ready thingy coming back, and we got our data coming across, and then a response. And that brings us into our exchanges. Our exchange, again, is a set of one or more related sequences for a single operation. And again, this is the fundamental way for coordinating the exchange of information and data between two imports. Again, all data transmission is part of an exchange. And this is what an exchange looks like. Again, we got one or more sequences containing X number of frames. And all frames within exchange are delivered in order. We've had a lot of discussion on in-order delivery in Fibre Channel lately. And this, in the case of a change in a fabric topology, for example, a link is removed from or is introduced into a fabric topology, in-order delivery may be temporarily suspended, and out-of-order delivery may occur. And still on sequences or exchanges again, then sequences for the same exchange may flow in the same or opposite direction between a pair of imports, but not simultaneously. And data flows in one direction at a time within an exchange for a single import pair. And exchange may be unidirectional or bidirectional. It either doesn't have to be a response on a unidirectional thing. And within an exchange, or within a single exchange, only one sequence is active at any given time for a single initiating import, i.e. the sequence initiator completes transmission of data frames for a sequence before initiating another sequence for the same exchange. And that brings us into our protocols, where I kind of lumped them into different categories here. We got our set of primitive sequence protocols. These are all based on primitive sequences and are specified for link failure, link initialization, link reset, and online to offline, or online to offline transition, excuse me. Then we got our fabric login protocol. Again, we talked about that, where the import exchanges service parameters with the fabric. This creates the first V import associated with the P import, physical import, and the fabric. And it is an explicit procedure, i.e. it's a floggy ELS that completes successfully. And it's sent in again in an exchange that completes with an LX accept. Then we got our additional import ID protocol. And this creates additional V imports associated with the P import and the fabric again. And again, it's an explicit procedure using floggy that completes successfully. Then we got our import login protocol, which before performing data transfer, the import exchanges service parameters with another import. And again, it's another explicit procedure. That's the P loggy that we mentioned that completes successfully. And finally, we got our data transfer protocols. And that's the UOP data is transferred using data transfer protocols specified in the various FC4 standards. And again, we mentioned FCP5, SP6, NVMe2, those types of protocols. Then when we're done, we got our logout protocol. And that removes our service parameters from another import or the fabric. And again, it's an explicit procedure. It's a logo ELS that, again, completes successfully. And with that, I'm going to hand the reins over to Patty.
Okay, thanks, Dave. So Dave took you through some very low-level aspects of Fibre Channel, and those are the critical details behind how Fibre Channel basically works. I'm going to try to take it up just one level and start with describing how some of these things like frames and sequences come together and are used in upper-level protocols. So these upper-level protocols are then mapped to the Fibre Channel transport, and each of them has their own standards that are developed through ANSI and through Insights. Each ULP defines how information particular to that ULP is going to be packaged for transport. So whether it's commands or data or control information, they're all packaged into something called information units, or IUs. And FCFS has certain rules about how IUs are formed and how they relate to sequences and frames, but it also leaves some flexibility in terms of how that mapping is done. So the specific content of the IUs is defined inside each of those FC4 standards, whether it's FCP or FCNVMe or FCSB. And then those IUs are decomposed into sequences and frames following those fiber channel rules. And some of the rules are shown here. Dave talked about others, but IUs don't span sequences, although the sequence containing IU can be composed of multiple frames. So Dave introduced you to this R control field of the fiber channel frame header. And this field is very critical in the definition of those IUs. So you may remember Dave said that the R control field is a 1-byte field, but it's broken down into 2 4-bit fields, the routing and the information category. And as noted on the chart, all FC4 IUs are transported in frames with the routing subfield set to 0, which is device data. But the information category subfield is used at the discretion of each FC4 protocol to then further classify how the IUs are treated. And there are a set of information categories that are defined in the FCS standard that these FC4s use. So things like you see here, solicited and unsolicited data, solicited control and unsolicited control, command status, and others. But exactly how an FC4 uses these categories to map their messages into IUs is fully within its discretion. What you'll see across the various FC4s is a lot of commonality, but there's also a fair amount of variation. So having said there's variation, I'm going to start with showing you some commonality. On this chart, I've selected a subset of the IUs that are defined in each of the 3 main fiber channel FC4s, FCP, FCNVMe, and FCSB. And just for reference back to what we talked about earlier, the information category, I list which information category the FC4s have used for those IUs. Now, FCSB has 2 modes of operation. One's referred to as command mode and the second referred to as transport mode. Command mode has some very unique IU mappings that I'm not going to go into here because that's a whole subject unto itself. But what I'm showing here is applicable to what's called FCSB transport mode. And what you can see from all 3 of these is that FCSB transport mode has a lot in common with FCP, as does FCNVMe. The 3 IUs defined for all of the 3 protocols are similar. Command, data, status, and control. All 3 define a similar means to deliver messages of the various needed types. But that doesn't mean that the content of each IU is identical. And I'm going to show you a little bit more detail example in just a minute. So I'm going to start with talking again about another field that Dave introduced you to, which is the type field in the FC header. And this field, as Dave mentioned, is to identify the protocol for which the content of the device in the linked data frames applies. So there's a type value of 8 for FCP, and there are other type values. SB uses 1 Baker and 1 Charlie for their command mode. There's one for fabric switch internal link services. But I'm going to focus in right now on the 08 FCP type. FCP was for many years the most prolific fiber channel ULP. So many host bus adapter chips designed in hardware assists and provided firmware accelerators to help the FCP protocol performance. Now, FCP is a transport protocol. It's a method of transferring command data and status. It doesn't equal SCSI, although SCSI is the largest single user of the FCP transport. in more recent years, 2 other ULPs have been designed and defined in such a way as to be able to take advantage of all those same accelerator functions for FCP by piggybacking onto some key components of the FCP transport. And those 2 FC4s are SP transport mode and NVMe. They both reuse that type 08 field. And they also use a subset of the same SCSI FCP IUs. They use the same ARC control values. And so to an HBA, these additional link transport protocols look the same as FCP. But again, kind of looking the same, using key critical features and bits and bytes, nevertheless doesn't mean that the entire content or definition of the IUs is the same. So let's explore an example here using this chart. So what I did here was I depicted side by side the command IUs for FCP and for SP transport mode. Now, I did this. SP was the first protocol to do this type reuse, right? Taking the type 08 field. And so since they were first, what they did was felt the need to map as close as possible to that existing FCP structure. So when you look at the command IU for SP transport mode, it looks a lot like the command IU for FCP. The orange part is the fiber channel header. And following that in FCP is the addressing information for the target device. In FCP terms, that's a LUN. Or in SCSI terms, it's a LUN, right? For in the SB world, again, it's a different language, different protocol, different language. And so things known as a control unit image ID and a device address or unit address are needed to fully specify the target. But they both use the same words, the same bytes to place that addressing information. You'll notice SB always places a value of FOXeasy in the first byte, which for FCP is the LUN address. In the FCP standard, that value of FOXy is reserved for SB, and a value of FOXdog28 in the first 2 bytes is reserved for NVMe, FC NVMe. So if either of those 2 values are present, then the payload of that IU is interpreted as it's defined in that respective standard. Otherwise, it's interpreted as what you see here for FCP. Again, SB in the next section tried to keep things as constant. It basically kept the information in the last byte constant, which is the additional length of the command descriptor block and the read-write operation bits. The green area is the command descriptor block, and that's very similar. It is a command descriptor block and called that in both of them. And SB always uses a variable length CDB, so that's what the 7FOX in that first byte references. And then there were service action codes that were reserved in the SPC, the SCSI primary command specification, for SB's use. So, and the area in red is basically where the actual commands that are being transferred for SB are contained, but it's that additional CDB area. So you see here that SB tried to keep true to the spirit, if not the exact content of the FCP command IU definition. Now, I don't have a picture here of the NVMe command IU, but if you were to do a side-by-side comparison of it next to the FCP command IU, you'd see that FCNVMe felt no obligation to maintain that same level of synergy with the FCP-IU content. Basically, after the FOXdog28 in the first byte, there's really little resemblance between an FCNVMe IU, command IU, and an FCP command IU. But again, some commonality, they maintain the same type field. Okay, so moving on to segmentation and reassembly. So now that we've discussed how the ULPs transmit their data and messages in IUs, we can discuss another concept related to the rules in FCFS for features that control segmentation of IUs into transmitted frames and the reassembly of those frames into IUs on the other side. So as we said earlier, each IU is transmitted within a single sequence, but it may be divided up into multiple frames. And all frames with the same information category within a single sequence must be reassembled into the IU for delivery up to the FC4 layer. There are two methods that are defined in the FCFS spec for segmentation and reassembly. You can do it using sequence count or relative offset. To use either one of the methods, a particular method, both endports must support that method. And those methods, which method you're going to use, is negotiated during PLOGI using the common service parameters. The sequence count method needs to be supported by all endports, whereas the relative offset method is optional. As Dave did mention, but kind of reinforcing here, the method specified by sequence can be on a sequence basis or on an exchange basis. So which you're going to do, relative offset or sequence count, is based on the setting of the relative offset present bit in the F control field in the header. So when you turn on relative offset, the bit is set, you're using relative offset. If that bit is set to 0, sequence count is used. Since you're using the method to segment and reassemble all the frames within a sequence, then obviously the value of that RO bit needs to be the same in each frame in the sequence. So the other method that you can use is sequence count, or let's look deeply at sequence count. So sequence count is a 2-byte field that identifies the sequential order of the frames, again, either within a sequence or across multiple sequences in the same exchange. And it's negotiated, whether you're doing it per sequence or per exchange, is negotiated at PLOGI time. The sequence count for each frame in the sequence obviously has to be unique. Since it's a 2-byte value, it can range from 0 to 64K and then wrap back to 0. So when you're using the per sequence method, unique sequence count per sequence, that sequence count is essentially a frame count within the boundaries of the sequence, which means that if more than one sequence is required to transfer the data, then the first frame in each sequence starts with a sequence count of 0, and each subsequent frame increments that count by 1. When you're maintaining the sequence count per exchange, then it's essentially a frame count within the boundaries of an exchange. The other option is to use the relative offset method. And an endport that's able to specify the relative offset of frames has two choices. They can either support continuously increasing relative offset address order or a random relative offset address order. And each portion of the IU specifies its beginning relative offset, and the beginning relative offset of each portion of the IU, when it's random, can be independent of the other relative offsets. Again, which you're using, continuously increasing or random relative offset, is negotiated at PLOGI time, and it's really up to the discretion of the FC4 which it supports. So some FC4s may require one or the other, or may support both. Remember again that the default is if you don't specify that you're using relative offset, then the frame segmentation and reassembly is done using sequence count. So the last thing we'll touch on is error detection and recovery. Link integrity and sequence integrity are the two fundamental levels of error detection in the FCFS standard. I'll start with link integrity. Link integrity focuses on the inherent quality of the received transmission signals. So when the integrity of the link is in question, when the integrity of the signals being transmitted is in question, as Dave mentioned, there's a hierarchy of primitive sequences that's used to reestablish link integrity. And those primitive sequence protocols when they're performed, it may also cause the need to perform recovery on a sequence basis also. So let's talk about sequences. Remember that a sequence within an exchange that's comprised of one or more frames, that is the basis for ensuring the integrity of the IU that's transmitted and received. Remember, at the end of the day, the FC4 needs to understand, be able to interpret what came across the link, which comes across to it in IUs, right? The frames make up sequences, and an IU is transmitted in there. So the sequence, the integrity of the sequence is key. And the sequence management and integrity involves ensuring that the sequence was properly initiated, it's properly ordered, if there are multiple sequences using the sequence ID, that frames within a sequence are properly controlled by the sequence count, and then that the sequence is properly completed. When one of those things isn't done properly, then frame errors can be detected in a couple of ways, or three different ways. You can detect a missing frame, you can detect a sequence timeout, or you can detect something wrong with the frame that could be a rejectable condition within the frame. Something didn't follow one of the rules. Now, what's done as part of sequence recovery is really under the control of the FC4 upper level. And within that FC4 upper level, there may even be options for specific implementations to choose from. But what the FCFS standard provides is the mechanisms and the procedures that can be deployed to perform the necessary recovery. Again, the ULP has control over which of those mechanisms and procedures it supports. So I'm going to hand it off now to Craig, who's actually going to talk about some more recent enhancements in Fibre Channel, and one of these is in fact a specific sequence recovery mechanism. So Craig, you can take it over.
So I'm going to talk a bit about some of the current enhancements underway within Fibre Channel. First of all, I'm talking a bit about this Fibre Channel security protocol. I'm going to talk about new speeds coming up, the sequence level error recovery that Patty just mentioned, fabric notifications, and VMIDs. So a little bit of history about Fibre Channel security. Authentication and encryption have been part of the Fibre Channel standards since 2012, and they are defined in the FCSP2 and the follow-on FCSP2 Amendment 1 standards. These protocols use the same ESP security header as defined for TCP/IP, and they provide for end-to-end authentication and encryption at the transport level, which is the data on the wire. They've already showed this, but I'll show it again. The example frame for what an ESP frame looks like. So we have, the top part, the standard Fibre Channel frames, extended headers, and so on and so forth. Then we have the ESP header, which is based on what is defined in TCP/IP, and this is defined as a Fibre Channel optional header. Following that would be an encrypted payload, and then there's a ESP trailer, and that's also as defined for the TCP/IP security. So some updates. We have opened up a new security project. The primary goal of this is to update for new security standards. In particular, the TLS and TLS 1.0 and TLS 1.1 protocols have been deprecated, and they're now, the favorable ones are now TLS 1.2 and the brand new TLS 1.3. And so the standard, we're updating the standard with FCSP2 Amendment 2, which is going to incorporate these new TLS versions. This is to make sure that we maintain Fibre Channel security with current security standards. And the next, exciting new thing coming up for for Fibre Channel is the FCPI 8 standard, which defines 128 GFC. This is based on the 100 gigabit Ethernet speeds as defined in the 802.3 standards, which is Ethernet. The goals of this continue to be, as we've had for previous speeds, is a plug-and-play backward compatible for at least the previous two speeds, which is done through our automatic speed negotiation. Our goal is to have similar distance in cabling requirements as exists for 64 GFC, and the completion of the standard is targeted for early 22. Sequential error level error recovery, as Patty mentioned, is a error recovery mechanism which is above the basic recovery mechanism defined in Fibre Channel. It was originally developed for FC NVMe 2. It allows for fast transport level error recovery from frame errors. And in most cases, when this is being used, the upper level protocol doesn't even know any error occurred. FCP5. Now, I noticed there was a question about the confusion of FCP5 about the name of FCP. The FCP-number set of standards define the SCSI over Fibre Channel protocol. The other standards borrowed the FCP data engine to move data. So FCP5 does define SCSI over Fibre Channel. It's the new revision. It's currently in the approval process. The slur mechanism has been ported to SCSI as well. And the reason we've done this is, while SCSI does have an error recovery mechanism, the slur process does allow for a potentially faster recovery, where slur can recover in a time frame of seconds. The SCSI process can be longer in many cases. So, just a quick example here. Send a read command, and so this could be an NVMe command or a SCSI command, and it's lost. And after a certain amount of time, a flush timeout, the initiator recognized it has not received a response to that command. So the initiator will then send a flush command, which is a new basic link service that we define for the SLER mechanism. The target will say, well, I haven't received anything that goes along with this flush command. It will send that response back to the initiator. So the initiator then will resend the original command. So response is the same thing. A NVMe command is sent, or a SCSI command. The response comes back, but it's lost. Once again, the initiator will detect that there's an error and will send a flush saying, "Hey, something's wrong here. I have not received what I expect to receive." Then the flush response will come back, will be resent by the target. And so the next enhancement that we're looking at is something called fabric notifications. This is a mechanism that allows the fabric to send notifications about issues that may be occurring in the fabric. There's two types of notifications. There are notifications which are based on ELSs and signals. Notifications are registered events, and they can give the more information to evaluate what is going on. Signals are low-level primitives, and their usage is to be an out-of-band signal that resources may be depleted, frames may be getting backed up, so on and so forth. The history of fabric notifications is the issue has been, this is a common issue in any sort of networking protocol, and so with something that was started to be investigated back in 2014, there was some research on it, and then in 2018 the standardization of it started, and in the last 2 years this has been rolled into the Fibre Channel standards, and I would expect to see these mechanisms in devices fairly soon. And then we have the mechanism for virtual machines, which has been which uses the application header, and this is the VMID, allows for registration and identification of virtual machine flows within the fabric. And with that, I'll pass it on to Dave Rodgers.
Thank you, Craig. We do have some great questions coming over the course of this presentation. Let me start with the newest one first, because it's germane to what you were talking about right there, Craig. Was does the OS need to resend the FC command that was flushed with slur, or is that done by the end port without the OS on the HBA?
Craig, do you want to answer or me?
I wonder if we lost Craig for a minute. Dave, go ahead and jump in. I know it's.
Well, yeah, the OS does not resend the command, so it's done down at the transport level. You know, it's done at that level. So the goal is to not send an error up to the OS level. So the command will be resent at a level lower than the OS.
Yeah,
So the OS offloads that transport to the FC protocol, and the FC protocol takes over from there.
Yep. The OS has no idea that there was a problem on the wire.
Yeah, so basically SLER is a transport level recovery mechanism. The OS does not have any knowledge that, or the upper level protocol, that any error occurred, and that's why the recovery mechanism can be as fast as it is, which within a matter of seconds.
And that's the inherent beauty of that particular recovery protocol as well, because now it does take the burden off of the OS, so that's pretty good.
Yeah.
Second question. Go ahead, Dave. Sorry.
I can expand on that a little bit just to clarify. So, yeah, there is error recovery, earlier on in FCP4, right? But that was basically done at the exchange level. And, with exchange-based routing, then things may not work properly. So that's why we develop sequence-level error recovery. So all the recovery is done within the exchange. So we don't have multiple exchanges determining what to do for recovery. So that's a big difference. That's why we call it SLAIR. And the other one we call rec-based error recovery from the standards perspective.
But slur is just much faster and more efficient, and that's part of the beauty of that particular implementation, right, Dave?
Well, yeah, it's done within the exchange, but from a high level, it's the same functionality, but it's all done within the exchange.
Well, in the Segways RS category, the other question we have here is regarding FCP4. It says FCP4 equals SCSI, or FCP equals SCSI, question mark. Isn't FCP4 and such standardized by T10, and that is SCSI? How does that play with other standards also being FCP in quotes, instead of just letting them, let's just call them FCNVMe?
The
point is,
I touched on that a bit. The FCP standard is basically, the FCP set of standards defines, that's correct. In T10, they define SCSI. But the others, the FCNVMe and FCP, or FCSP, SB protocols have reused the data engine from the FCP SCSI standard. So I know there may be some confusion. The names are the same, and you have to keep in mind that the FCP standard itself defines mapping of SCSI over fiber channel, and the FCP data engine is what the other protocols are using.
Yep.
Right. So the way I say it is SCSI is really a device architecture, and FCP is SCSI over fiber channel, as I said, right, over that fiber channel transport. And SB and NVMe borrowed the transport mode by piggybacking onto some key FCP transport components. But within the FCP spec, they utilize some reserved value. So even in the FCP spec, it says if the first 2 bytes are FoxDog 28, then how you interpret this stuff is go oversee FC and VME, right? So it is, so SCSI is a device level thing, but FCP is a transport for SCSI, designed specifically for SCSI, but the others piggybacked over that transport.
Yep. Yeah, so for further clarification, you can go to Annex F and FCNVMe 2. So we have some clarification text in there. Basically, it says if the first, for command IU identification, if the first byte of a frame with type 08 hex with IU category will set to foxdog hex, that's reserved by T11, then the second byte, which we also define by T11, identifies the protocol, which defines the structure of the command IU. So that's how we parse things. That's how things are differentiated. And for FCNVMe, then that value is going to be 28. So that's how you figure out what the thing is on the wire. And so take a look at that, which also clears some stuff on the LUN field usage too.
Is some of this carryover from when we used to have actual Fibre Channel Connect drives that were using SCSI protocol?
Well, basically, all we're doing is reusing the FCP data engine for other.
Okay.
In a nutshell, and we've done that in a couple of different fashions, as Patty mentioned. The ESP format is a little slightly different than
Perfect.
ME, but in the end, everything's using the 08 data engine. And yeah, we can just, that's how we can easily reuse things over Fibre Channel using the same engine.
Well, I hope that answered the questions. I don't see any edits or response to that, but I think that was, it can be confusing. I think we have a blog from Barry Maskus talking about the alphabet soup of acronyms at some point in time, and things can get a little confusing when we have so many different protocols and specifications talking about common protocols. So if we don't have any more questions, just a quick kind of housekeeping, cleaning up after here. We would love to hear from you relative to your how you felt this webcast went. Please rate the event. We do post all of our videos on our Q&A blog at fibrechannel.org, and so we will have a answers Q&A will be posted there for what we extract from this webinar. Please do follow us on Twitter at FCIA News for future updates about our webcasts. We do have a pretty extensive library of existing webcasts, and we've been doing this for more than a minute. So if you bop onto the fibrechannel.org/webcasts, you'll see a whole bunch that we have in there, so you can refresh and review some of the content that we've put together in the past, which it's very helpful, and we seem to get a lot of repeat visits to that. So I think it's really, I know it's really great content and good information. It's either a refresher or for somebody who's just getting into the protocol for whatever reason. And with that, if we don't have any more questions, I'll throw it out to the panel if you got anything else you want to wrap up with or closing thoughts. Otherwise, I think we can call the ball and everybody can have a great day. Dave, you got anything else?
No, I got nothing. Have a great day.
Mr. Carlson?
Nothing else?
And last but certainly not least, Patty, you got anything, any closing comments?
No, just thank everyone.
That's awesome. Okay, well, guys, thanks again. We look forward to having you folks attend our next event, and have a great rest of your Wednesday. Cheers.